Introduction to Feedback Controller. Today, almost every intelligent system around us, from autonomous cars and drones to industrial robots and smart buildings, relies on one fundamental idea. That idea is feedback. Feedback is one of the most powerful concepts in engineering because it allows a system to continuously observe itself, learn from its behavior, and make better decisions. In this video, we are going to build the intuition behind feedback control. We will see what closed loop control really means, why feedback is so important, and finally, we will build a roadmap that will guide us through all modern control methods in the next videos. So, closed loop control. Let's start with the basic feedback loop. Every control system begins with a reference, which represents what we want the system to achieve. We compare this desired value with the actual output of the system. The difference between them is called the error. The controller receives this error and decides what action should be applied to the system. The system responds, sensors measure the new output, and the whole process repeats again and again. This continuous cycle is what we call closed loop control. Instead of acting only once, the controller constantly monitors the result and corrects its behavior. But why do we even need feedback? Imagine driving a car with your eyes closed. You can press the accelerator or turn the steering wheel, but you never know whether the car is actually following the road. That is exactly what an open loop system does. It sends commands without checking the output. A closed loop system is different. It continuously observes the result of its actions. If disturbances occur, or if the model isn't perfect, it automatically compensates from them. This is why feedback makes control systems much more accurate, robust, and reliable. Controller map. Now that we understand the feedback, let's look at the bigger picture. Over the past decades, researchers have developed hundreds of different control algorithms. At first glance, this can seem overwhelming. So instead of studying them one by one, it's useful to organize them into a simple map. This map classifies control methods along two dimensions. The horizontal axis represents the source of knowledge. On one side, controllers rely mainly on mathematical models. On the other side, they learn from data. The vertical axis distinguishes between traditional engineering methods and modern AI-based approaches. This gives us four major families of controllers. The four quadrants, each quadrant represents a different philosophy for solving control problems. Model-based traditional methods use physics and mathematical models to design controllers. Model-based AI methods combine physical models with learning or adaptation. Data-driven traditional methods rely more on measured data than on explicit mathematical models. Finally, data-driven AI methods learn directly from interactions with data and the environment. None of these approaches is universally better than the others. Each one is designed for different types of systems and different engineering challenges. In conclusion, so what should we remember from this video? Feedback is the foundation of modern control systems. Closed-loop control allows systems to continuously improve their behavior, and the controller map provides a roadmap for understanding the wide variety of control methods availability today. In the next video, we will start exploring the first family of controllers, PID controller.